Hi, welcome back to my channel. My name is Gina. In this video, we are going to look at two examples to determine whether a vector can be written as a linear combination of the other vectors. Let's start with the first one. Here we want to determine whether the vector b is a linear combination of b1 and b2. If so, how can we write b as a linear combination of them? In other words, we want to find whether the vector b is in the plane spanned by b1 and b2. If we can write b as a linear combination of the two vectors, then we should be able to write b as some scalar times b1 plus some other scalar times b2. In other words, we must solve the following equation: x1 times b1 plus x2 times b2 equals to b, where x1 and x2 are the coefficients in front of the vectors. So we can rewrite the system in augmented matrix form. The system has augmented matrix. The first column is b1, 1, negative 2, and 0. The second column is b2, 2, negative 1, and 2. And on the right, we have the vector b, 3, negative 12, and negative 4. Where the first column is multiplied by x1, the second column is multiplied by x2. So the next step is to reduce the matrix. First of all, I'm going to replace row 2 by row 2 plus 2 times row 1 to eliminate the negative 2. Then we get 1, 2, 3. Then the second row is 0. Then negative 1 plus 4, that is 3. And negative 12 plus 6, that is negative 6. Third row remains the same: 0, 2, and negative 4. Then I have my first pivot ready. In the first column, other than the pivot, all the other entries are 0. Now moving on to the second pivot, it will be in the second row, and I want my pivot to be 1, so I'm going to replace row 2 by 1/3 of row 2. First row remains the same, 1, 2, and 3. Second row is now 0, 1, and negative 2. Third row also remains the same, 0, 2, and negative 4. Then to eliminate the 2's in the second column, I'm going to replace row 1 by row 1 minus 2 times row 2. And the same for row 3. Then the matrix becomes 1, 0. Then 3 plus 4, that is 1. Second row remains the same. Third row is now 0, 0, and 0. Now the matrix is in RREF. We have the first pivot here and the second pivot here. So from this matrix, we get x1 equals to 1 and x2 equals to negative 2. So to answer the question, yes, we can write b as a linear combination of b1 and b2. If we substitute x1 and x2 back to our system, then we can rewrite b as 1 times b1 plus negative 2 times b2. And it is now written as a linear combination of b1 and b2. Now let's look at the second example. It's similar to the first example. We want to represent b as a linear combination of vectors, but now we have 3 vectors. So we want to solve for the system where b can be written as x1 times b1 plus x2 times b2 plus x3 times b3. So the augmented matrix for the vector equation is as follows. The coefficient matrix has b1, b2, and b3 as the columns. And on the right of the vertical bar, the constant vector is our vector b. Now let's reduce this matrix. I already have the first pivot that equals to 1. So to reduce the other entries in the first column, I'm going to replace R2 by R2 minus 2 times R1 and replace R3 by R3 minus 3 times R1. Then, first row remains the same, 1, negative 1, 1, and 3. Second row is 0, then negative 1 plus 2, that is 1, and 4 minus 2, that is 2, and negative 4 minus 6, that is negative 10. Third row we have 0, negative 2 plus 3, that is 1, 5 minus 3, that is 2, and negative 6 minus 9, that is negative 15. Now I have my first and second pivot both equal to 1. Next step is to reduce the other entries in the second column. However, I can already see that in the coefficient matrix, the third row is a scalar multiple of the second row. So if I perform the elementary row operations, I'll get a row of zeros in the coefficient matrix. For example, if I replace R3 by R3 minus R2, then I get 1, negative 1, 1, and 3, 0, 1, 2, and negative 10. And the third row, I'll get 0, 0, 0 in the coefficient matrix. But on the right, I have negative 15 plus 10, that is negative 5. The third row is saying 0 equals to a non-zero number, which means the system has no solution. So the vector b cannot be written as a linear combination of v1, v2, and v3 because we are not able to find a solution to the vector equation x1 times v1 plus x2 times v2 plus x3 times v3 equals to v. And another remark, since here we have 3 vectors in R3, and we are not able to find the linear combination form of another vector in R3, which means the 3 vectors do not span the entire R3, so the 3 vectors must be coplanar. In this example, the vector v does not lie in the plane that's spanned by the 3 vectors. And that is the end of the video. If you like my videos, please like and subscribe, and I'll see you in the next video.